Okay, let's try another example here and see how this one goes. And there's going to be a little bit of variation in this one compared to the first one. So now you'll notice as we look at position 1, 1, we don't have a 1 in this position. So our options are one of two things. Either we can divide everything by 2, which would introduce a bunch of fractions into our matrix, which we really would prefer not to do. So let's not do that. But we do notice that there is a 1 as the leading element in the second row. So we can interchange row 1 and row 2, and that will give us a 1 in that first position. So let's go ahead and do that. So we'll have 1 minus 2 minus 2 minus 2 as our new top row. And we're going to have 2, 3, negative 4, 3 is our second row. And we'll rewrite the third row. And now we can start working on those row operations to eliminate the elements that are in that first column there and turn those into zeros. So we'll multiply, to get our new second row, we'll multiply the top row by negative 2 and add it to the second row. So that's going to be minus 2 times row 1 plus row 2. And again, we're happy here with the top row for the time being. So I'm going to rewrite that one. And we're just replacing row 2 and row 3. So let's go into our routine. We do some multiplication addition. So minus 2 and 2 is 0. 4 and 3 is 7. 4 and negative 4 is 0. And 4 and 3 is 7. So there's our new second row. To get our new third row, we'll go ahead and just add row 3 and row 1 together. So row 1 plus row 3, and that'll give us our desired 0 in that spot. So let's add them up, and we get 0, 14, 0, and 14. And you're kind of probably noticing that equations 2 and 3, or rows 2 and 3, look pretty similar, and we're definitely going to use that to our advantage. But it's also going to create a specific situation that we need to be aware of. So let's go ahead and follow the procedure, which is to now make a 1 in position 2, 2, the next diagonal down. And we can do that by just dividing everything by 7. So rewrite our top row. And now we get a second row that looks like 0, 1, 0, 1. And while we're at it, maybe we'll go ahead and make the bottom row 0, 1, 0, 1 as well. So now I end up with this new second row coming from 1/7 times row 2. And in the bottom we did 1/14 times row 3. We didn't necessarily have to do that, but we can see that that actually turns out to be kind of a benefit in this situation. So now we do as we would typically do, try and turn everything else into column 2 into a 0. And we can do that. Let's go ahead and set up our matrix and rewrite row 2 now. And we'll go after a new top row and a new bottom row. So we'll multiply the second row times positive 2 and add it to the top row. So 2 times row 2 plus row 1 will give us our new top row. 2 times 0 is 0, plus 1 is 1. 2 times 1 is 2, minus 2 is 0. 2 times 0 is 0. Minus 2 is minus 2. And finally, 2 and negative 2 is 0. So there's our new top row. The new bottom row we'll get by taking minus 1 times row 2 and add that to row 3. So minus row 2 plus row 3 is our new row 3. Minus 1. So here we go. 0 and 0 is 0. That's from that part. Minus 1 and 1 is 0. 0 and 0 is 0. And lastly, 0. So in this case, we get a row of zeros all the way across the bottom. And we're actually in reduced echelon form here. It fits the form according to all the rules that we have. And that means that we're done in terms of solving. There's really nothing else to do. That bottom row turned into 0, so there's no way I can make that into a 1. And as a consequence, regardless of what these two numbers are, I could no longer make those into zeros as a result of that. So we are finished with our solving process. Now we just have to interpret the solution. So if we think about what each one of these rows is telling us, from the top row I end up with x1 minus 2x3 equals 0. The second row is telling me that x2 is equal to 1. And the last one says that x3 is equal to x3. So x3 ends up being what we refer to generally as a free variable. And we then try and rewrite all the other expressions in terms of that free choice variable. So this is an infinitely many solution situation. And you'll remember from our systems of equations, we had some specific language for that. So it was consistent and dependent in this case, because the answer will depend on what we choose for x3. So let's just do this one more, let's just do this additional step here and rewrite x1 equal to 2x3. x2 is fixed at 1, and x3 can be whatever we want it to be. So this now represents what we would get for our solutions. And just as an example, we could take any value we want for x3, but let's just say take x3 equal to 2 or something like that. That means that x1 is equal to 4, x2 is equal to 1, and x3 is equal to 2. So that gives us just an example of one of the solutions to this system. As an additional maybe practice here, let's just take x3 to be equal to 0. Then that means that x1 is equal to 0. x2 is fixed at 1 again, and x3 is equal to 0. So this represents another solution. Of course, again, we can take x3 to be whatever we want it to be. So we end up with infinitely many solutions here. And again, this is how we describe that solution set in terms of its free variable.